Welcome back friends, welcome to another video tutorial from Shomu's Biology. In this video lecture, we'll be talking about IR spectroscopy, which is also known as infrared spectroscopy. You know, infrared is belonging to our normal electromagnetic wavelength. If you look at the wavelength, it is a large wavelength. It's much bigger than the visible wavelength that we can see. So that's why we can't see infrared, but this infrared light can be very beneficial for understanding the structure of different chemical compounds, especially the structure of different groups or chemical groups of those molecules. So IR spectroscopy is also known as vibrational spectroscopy or the chemical group or group related spectroscopy. Now what does that mean? IR spectroscopy depends on, or it actually helps us to find out the structure of different chemical groups that are present in a molecule. Mostly the functional group, and the presence of functional group can be very well detected with the help of IR spectroscopy. For understanding the structure of unknown chemical compounds, we have different techniques. We have NMR spectroscopy, we have X-ray crystallography, we have mass spectrometry. But this IR spectroscopy is not that powerful to give you data about the whole chemical compound, but it is good enough to give you an idea about the functional group that are associated with the target molecule that you are experimenting with. So let's go into it. IR spectroscopy works in a very simple principle, and that principle is the bond between the different atoms. The atoms that are present in a chemical compound, they are bond or linked with each other, either with a single bond or double bond or even triple bond. So those molecules can have saturation or unsaturation. About the whole process, it depends on how those bonds are behaving. Because if you look at the bonds, if you look at a chemical compound and atoms are linked with bonds, those bonds are not permanent, it's not fixed. They are always involving with different type of motions. That could be vibrations. They are known as those bond vibrations. The vibration means, let me give you a simple example. If we are talking about a carbon attached with a hydrogen, for example, or let's say carbon attached with a nitrogen or oxygen, for example, that interaction, it could be with a single bond or it could be the interaction with a double bond, but in any sense you can imagine that these two atoms, they are linked with not a simple line. You can think of it as a spring. So that means if you imagine this is attached, it's attached attached with a spring with an oxygen. So now you think this spring can go from each other towards each other, or it can come towards each other like that. So the spring can be like dragged opposite to each other, or sometimes can be towards each other. So by this fashion, what we can see is an oscillation. You can see this sort of oscillation that is known as wagging. That's not wagging, that's kind of a stretching, we can say. It is known as stretching. So this bond, they can have a stretching effect if you can take it away from each other and also bring them close to each other, just like a spring will do. Stretching is always going on in all those bonds. There is also another effect known as wagging. What is that? For understanding that, let's take one compound as an example, and that is, let's say, formaldehyde. Formaldehyde, if you take, this is the structure of formaldehyde, where carbon is attached to this oxygen. This is a carbonyl carbon, because this is a carbonyl group that we can see here. This carbonyl group, if we talk about, this particular carbonyl bond, forget about the hydrogens here, this particular carbonyl bond, if you look at here, just imagine the carbon is attached to the oxygen with a spring. So there is a stretching effect. So they have a stretching effect between this carbon and oxygen. They stretch like this over here. And also there is another effect, that let's consider this as oxygen is attached to the carbon, and just like this, it can also rotate in a zigzag fashion like that. This is known as wagging. This head is moving like this. So this is the wagging movement like that. So we have wagging and we have stretching here. Two type of effects that we can always see. So in this chemical compound, you will see always this stretching and wagging going on. Now there is a frequency by which the stretching continues and the wagging continues. Normally in case of this formaldehyde, the stretching is 2 Hertz and the wagging is considered as 4 Hertz. For example, say Hertz is the frequency with which this stretching or wagging is taking place. For the stretching, the frequency is 2 Hertz. For the wagging, the frequency is 4 Hertz, for example. Now what we see here for this compound, this type of rotation and vibrations around the bonds are very important for giving us the idea about the type of functional group we are looking at. Whether the functional group is carbonyl carbon attached, or it could be like any other type of bonds attached with it. There are different types of signature movement and signature vibration and stretching for different types of bonds. If it's a double bond, there's a kind of stretching. If it's a single bond, a different way of stretching. If it's a triple bond, that's another different kind of stretching. So those variations among those chemical compounds are going to give us so many different varieties of data, which will help us to find out what kind of compounds we're talking about. Because I told you, our job for IR spectroscopy is to find out a target group, functional group. That's what we need to find out. Now what exactly IR spectrometer does, let's look at here. Let's take this compound as an example. And what we do here in the IR spectrometer, that we simply put infrared radiation. Let's say this is the gun, infrared, this is where the infrared comes in. We simply write it as a light source because it is light source, just we can't see it because it's having a longer wavelength over there, and also the wavelength number is also a little big here. So this infrared radiation, this light source is coming in, and this is the chemical molecule present here. So let me draw the chemical molecule like that. Now we can control the frequency of this infrared light that is hitting this compound. Let's say this IR is moving in a frequency of 1 Hertz. Now we know that in this compound, the vibrations and the stretching and wagging, all these movements are, none of them are 1 Hertz. The stretching is 2 Hertz, wagging is 4 Hertz. So as this IR is hitting this molecule in 1 Hertz frequency, it is not going to influence this molecule. So this compound is not going to absorb any of that. So it's going to emit all of it. This is the idea. IR is hitting it 1 Hertz. There is nothing going on in the 1 Hertz frequency in this molecule, no bond expression in the 1 Hertz. So all of this light that is passing through the molecule, it's completely passed. None of the light is absorbed. So at the end of this chamber, we have the detector. We always have detector at the end.